Hello. I've been meaning to make a tutorial for ILGPU for a long time. I've written some documentation, and I know I personally learn better from following along with the video. And so I thought I would make a more advanced project and walk everyone through it. The end goal is to encode an image with depth data into a voxel grid, kind of like a nerf, except not a nerf because we're not going to be doing neural network stuff, and then read it out from different perspectives. But before we do any of that, we need to output information to the screen. And my favorite way to test doing that is to write Conway's Game of Life. So if I run the example project I have right now, you can see we get a randomly filled grid. And if I press space, it updates according to the rules of Conway's Game of Life. And there we are. You can see it's filled with random data, so it just clears itself out. But it does that very, very, very quickly because this is out on the GPU. And we can even go over here and like change the scale. So let's do 2 times scale. So this is going to look terrible on the video, but we're going to do it. Here you go. We'll update it 4K. Wow, that does look terrible. But there you go. That's what our end goal for today is going to be. So the first thing you want to do is start a new project. So I'm going to open a new solution, and actually I will I'll get rid of this. Goodbye. So we'll create a new project. We want to do WPF. We'll name it whatever you want. So tutorial. Hit next. We'll do long-term support. You might be able to hear my cats in the background. And then we'll wait for IntelliSense to finish setting everything up. There we go. So we need, we're doing this with the UI, with the WPF UI toolkit, which works fine. You can do this, you can output the buffer to OpenGL using something like OpenTK or SFML. There's a lot of other options. I'm going to use WPF just because I have code that does it already. It's not as fast as something like OpenGL because with OpenGL you don't have to download it from the GPU and then upload it to the GPU again. But at the buffer size we're dealing with, it doesn't really matter unless you're going like 500 FPS. So we're gonna create a new. I'm gonna create a new folder just because I love folders. We'll call it UI, and then we'll create a new user control. We'll call it render frame. And then that will open up the user control stuff. And then I'm going to switch my cheat sheet over to another thing. Okay. Okay, so our render frame starts as a blank control. We're going to add a couple things. Image. Gonna give it a name. Frame. I think you do a normal one. Yeah. Stretch, uniform, render options, bitmap scaling mode, nearest neighbor. Okay, that's good for that. Oh, we got to set the background of this to white. White. And then we want a label, just so that we can output some data to the screen about how much time our rendering takes. Foreground, we're going to do white again, background black, horizontal, this is left, and vertical alignment is top. And close that tag off. Okay, that's almost all of the XAML we're going to have to write for this. The WPF stuff we're going to clear out real fast, and then it's all mostly going to be ILGPU stuff. So don't really worry too much about how long that's going to take. We want our render frame to be able to have a scale so that the pixels in our Conway's Game of Life board aren't going to be too giant or too small and take up so little room that you can't really see them. So we're gonna put a double for the scale equals, we'll start with 2, -5. We'll start with 5 pixels per 5 pixels per pixel, like Conway's Game of Life cell, I guess is what they're called. Width, we don't set anything. Height. We want a writable bitmap. This is the thing. This is the thing that makes all of this super easy to write. It's a bitmap that we can give the in 32 rect. Sorry. So in the renderFrame.xaml, this image frame, we are going to give the writable bitmap, and that's what we're going to be able to basically, when we write to it, it updates the image in that frame for us automatically, which saves us copying a ton of stuff around. This view is also going to be what's in control of doing the resolution scaling. So this is actually going to drive almost the whole thing. I don't think we need the next one. Okay, so we're going to initialize the component and then render frame size changed. So we're going to create a, that's fine. We're going to create a, what are these called? An event handler, a size changed event handler, and then we're going to set the width with this. So width equals int e.new size dot width, and then we'll change height to that. And then update res. And we're going to make this function. Okay, so now here's where we do the scaling part. If the scale is less than 0, we're going to scale down. So height equals int height. Or sorry, if the scale is greater than 0, we're going to scale up. Less than 0, scale down. And then we'll do the same thing for width. Actually, I can just copy this. Oop. Not cut, copy. Divided by, and then we gotta negate the scale because it will be negative and we want positive numbers. But yeah, this means we don't have to have a value that says scale down to this thing or scale up to this thing. It can be just one value, the scale, which is, I find, easier. Width. Oh, and then we need a, this is a hack to make the bitmap a valid bitmap. Width times 3 or mod 4. So bitmaps need the width to be a multiple of 4, and if they're not a multiple of 4, the bitmap doesn't work because a multiple of 4 bytes is 32-bit aligned, and so if you don't 32-bit align the width of the bitmap, everything complains and it looks like garbage, and sometimes it just fails to be created. So if you do this, it's a hack. It changes the size of the bitmap slightly, but because WPF scales it for you, you can't tell, and it works super well, and saves us a shit ton of headaches. So I would recommend doing that. So this is now where we create the bitmap because we know what the resolution is. So we're going to create it with a width and a height and 96 dpi because that's the standard. And then the pixel format is going to be RGB pixel formats. That's what it is. RGB 24, which is 1 byte per subpixel and RGB subpixels. in that order, and then null for the palette, which is just a standard palette. And now we can set the source for in the XAML for this frame, we can set the source to this bitmap. And then we need to create a rect for when we change the data in the bitmap, and we want to change the whole thing. So we'll just create that now so we don't have to create it later. And now if that callback exists, we're going to invoke it with the width and the height. Okay, so that's it. You'll see in a minute how this all comes together, but effectively what's going to happen... Oh, wait, no, I'm lying. There is one more function that we need. Okay. The all-important function. Void update. Byte array data. Okay, so now we need the update function, which is actually going to write to the writable bitmap with the data that we download from the GPU. So the first thing we need to do is check if the bitmap is available, and if it is, we need to check that the data length is correct. And if the length of data is correct and the bitmap is available, then we can lock the bitmap, which basically locks the memory in place so it can't be moved around by the garbage collector. So then we get a pointer to the back buffer, and nope. Now we use Marshall, which we're going to have to add the include for, which is using system.runtime.interop services. So we're going to manually copy data into the back buffer. And the reason why we need to check that the length is correct is this is what the length of the back buffer is going to be, provided you do this hack up here. If you don't do this hack up here, it might be different. But this makes sure that data is the correct size, and then we can just copy the whole thing over. Add dirty rect. So now we need to tell it that the whole image, which is the rect that we created right here, is updated and needs to be copied over, and then we can unlock it. So now on that unlock call, the back buffer is going to be copied into that image in the render frame. And then we can also set the content of the info. Okay. So that's done. What's this complaining about? Oh, I'm missing a... There we go. Cool. So there, now render frame is complete, and we can close those two tabs. And then in main window.xaml, we're going to add the render frame. So let me make sure I do that correctly, because there's a trick to it. Yes, okay. So the weird thing you have to do is you have to add a reference to that UI folder. So it's xmlns, and then we'll call it UI equals CLR namespace tutorial.ui. Okay. So now from here we can create an instance of UI render frame. We'll give it an X name of frame, and that's it. Now we have all of the we have this user control added to our frame. What is it complaining about? Render frame does not exist in tutorial.ui. I think it does. misspell it? Is it just complaining? Let's see what happens when I build. Let's see if it still complains. Sometimes with these, yeah, it succeeded. Okay. Sometimes when you're using this XMLNS linking thing, you have to just build to get it to update the any of these comments about things not existing. But it exists, and the screen is black now, which is how we know. And so if we run, nothing's going to happen. But it should run, and we get just a black screen. That's exactly what we expect. Perfect. Okay. So now in mainwindow.cs, we're going to start doing ILGPU things. So first things first, every ILGPU program needs a context and a device. That's not going to work yet, though. We need to add ILGPU. So under dependencies, we're going to hit Manage NuGet Packages, and then we're going to click Browse, and we're going to search ILGPU. And then we're going to install the latest stable for ILGPU and for ILGPU.algorithms. So I accept. Then go to Algorithms, install that. I accept. Lightning and DX are old things that aren't really used anymore, so I don't really bother with it. Okay. And now we have ILGPU. So public context. And then you'll have to add ILGPU. And you'll have to add something for this, runtime. And then I'm going to add a function called initGPU, where I'm going to create the context and everything. And it's going to take a bool, which is force CPU, which we'll use for debugging. It's super handy. Forcing this CPU is a good way to go, because you can actually debug the CPU if you get random errors. So context equals context. Really wants to create that weird thing. Builder. So we're going to create a builder object that's going to get handed back to context.create. CUDA, because I have a CUDA CPU. I want to be able to use the CPU as well as an option. And enable. We want to enable algorithms. And for CUDA, we have to include using system or ilgpu.runtime.cuda. We're going to have to include something for CPU, and I think we have to include something for algorithms. No, we don't. Okay. So now device equals context.get preferred device. And we want to add for CPU. So get dot create accelerator context. Okay. So get preferred device looks through all of your devices and picks the best one. So in this instance, it's going to search through all of the CUDA devices and all of your CPUs. So I have one CPU, obviously, which is my AMD Ryzen CPU, and then I have my NVIDIA GPU, which is a 3070 Ti. And so it's going to check between those two, and if force CPU is enabled, it's always going to give you a CPU. If not, it's going to give you the most optimal GPU. So in this instance on my computer, I also have an AMD integrated GPU, which is active, and it won't pick that because it knows the CUDA GPU is likely to be more fast. You can also just pick yourself. There's different ways to query all the different devices, but in this instance, it just gives you the best one according to a heuristic. So we'll go with that. Just to make sure that is working, we're going to, we'll just put a breakpoint here, and we'll call this here. False, we want a GPU. Let's see what happens. Run the tutorial. Oh, I forgot. My breakpoint went away. I want a breakpoint there. All right, we'll restart. So we hit the breakpoint, and if we look at the device, it is my 3070 Ti. Perfect. So ILGPU is being completely initialized and is ready to go. Let us... now we have to deal with the hard part. The data structures. So we need to be able to write to a buffer of data. And you can manually control the buffers for everything and copy everything over. Or I like to have helper classes that kind of do that for you. And so we're going to build out my pixel buffer class. So we're going to create a GPU folder, and then we'll create a new class called pixel buffer 2D. Okay, and I'm going to open that up so I can go off my cheat sheet. So we're going to want to make this public, and then we're going to make this generic. So it's going to take a type T, and it's going to be disposable, and T, it has to be specific. So we want where T is unmanaged, because the only things you can put into a GPU with ILGPU are unmanaged T's, which is basically anything that is a struct and only value types. So no references, so which means no classes. You can't have a struct with a non-fixed array, things like that. This class is going to have two public things, the width and the height. And then a bunch of private things. Private. Oops. A private bool needs update and needs transfer. We're going to use these to allow us to just read and write to the pixel buffer, and then whenever we need to use it on the GPU, we're going to copy it to the GPU automatically, and whenever we want to read or write to it on the CPU, it's going to copy to the CPU automatically. This will save us a bunch of code elsewhere. And when we end up doing the nerf thing, this is going to save us a ton of code. All right, so now we need something to actually hold the data on the CPU. T-array data. And now we also need a struct to pass to the GPU. So we're going to make that down here. D. We're going to call that a D pixel buffer 2D type T, and also where T is unmanaged. So D pixel buffer 2D T. So there exists, so memory buffer 1D, which I need to add the include for, is the actual linkage to the GPU memory through ILGPU. And there exists a 2D version, but I find it, one, we need a continuous array to copy into the writable bitmap. But also I find it easier to manage the striding and everything else myself. You could also write this with a 2D memory buffer. This striding thing here also is a more advanced option. When in doubt, just use the dense one. That's your best bet. Oh wait, I don't need the T there. Accelerator. It really wants to generate this for me. Let me draw this again. Public pixel buffer accelerator. I don't know why this is happening. It's ridiculous. Int height, int width. Wow, that was a lot. But we got it. We got there. Okay. It's also complaining that things aren't written to yet. So data equals new t. So we're going to instantiate a new array of the t object, width height times 3. The weird thing about this is because it's a pixel buffer, we're going to assume you're using RGB subpixels, and so everything is going to be multiplied by 3, which you kind of have to watch out for. Device, okay, DT. So again, we're allocating 3 times the amount. Frame buffer equals new. So let's create the, let's fill out the frame buffer now before we start writing the functions for pixel buffer 2D. The D pixel buffer 2D. Let's fill that out now. This guy. So we'll scroll down. So that also gets an int width and height. And then it has an array view. Type T with stride 1D.dense. So the memory buffer is the CPU side linkage to the GPU memory. The array view is how inside kernels you access that GPU memory. And so whenever we do anything with the memory buffer up here in the CPU land, on the device struct down here, this gets updated. And so if we want to read and write from this array view on the CPU, we do all of that through the memory buffer up here. And then the D pixel buffer struct is how we access it inside kernels. You'll see that a bit later when we're accessing kernels. And I should make these public too. Sorry. And this is the frame. So I'm just going to generate the constructor because it's going to take all of those things. And then this will change to a memory buffer 1D. Frame.view. Okay. There we go. And so up here we can do width, height, and memory buffer. So now we're fully building out the pixel buffer 2D. Let us... right now we have an iDisposable interface on pixel buffer 2D because it needs to be disposable, but I'm not disposing it. Let's change that. The memory buffer needs to be disposed. That's the reason why we want to implement iDisposable. Okay. I like being able to access the pixel buffer as if it were an array, so we're going to include the array accessor override. And this is where the needs transfer and needs update is going to come into place. So public, or no, sorry, I don't need to do that. It's just get and set. So for get, if it needs transfer, we're going to memory buffer.copy to the CPU. So this copies out of this line, copies out of data into the memory buffer, which is what's on the GPU. And then it doesn't need transfer anymore. Return data index. There we go. And then we'll write a set as well, which sets needs update, which is the opposite of needs transfer. Needs transfer means we need to copy from the GPU to the CPU. Needs update means we need to copy from the CPU to the GPU. And then data index equals value. Look at this. IntelliJ is just, or not IntelliJ. IntelliSense is just writing all the code for me. Not really, but close. One other thing we need because of needs update is a way for the pixel buffer 2D class to know when the device struct is getting read from. So that's why the device struct is private. So we're going to need a getter for that. Get pixel buffer. Or we'll want get D pixel buffer. So again, if it needs update, then we're going to copy. That means the CPU is dirty, so we're going to copy from the CPU. And then needs update is false. And then return. But needs transfer needs to update. Needs trans. Transfer wrong? Yeah, I did. And then return frame buffer. Perfect. So that's filled out. And then oh. I blew something out. Okay, so if you remember the render frames update function down here. This update function takes a reference of a byte array, which means we need to, in pixel buffer 2D, we need to be able to get a reference to this data array. And so we're going to do that here. Public ref t array get raw frame data. So again, same needs transfer thing as reading from the array directly. So we can just straight copy that. And we're going to return ref of data. There's that. Okay, let me make sure we've got everything we need. Buffer t end of this done. Okay, yeah, so that's everything we need for the pixel buffer 2D class, which again, the CPU side of the buffer. But the GPU side, we're going to want some ways to access data and read and write data. And so I like to just fill those out. And also it's 2D, but we have a 1D index into the array. And so we're going to need things that let us either calculate the index from an XY coordinate or calculate the XY coordinates from an index. So we'll write those really quick. Public. So that is just int x equals index over y, or width. And then y is the same thing, but we divide. And then we need to return those. And we're going to It's interesting that it thinks it's backwards. That's makes me question whether or not my math is wrong, but I'm fairly certain it's right. Plus x. Scroll down a little bit more. All right, so now that we can get the indices from either versions, we're gonna write some classes to access the data. So tx, we're gonna access read the 3 subpixels at a time. I forgot something. Because I remember that thing I warned us about up here with the whole, we're multiplying it by 3 for the subpixels. I just almost fucked that up. I fucked that up in 2 places. Well, yeah. So we want subpixel. Yeah. And then we want to do the subpixel for this. So we want the subpixel for the X. And we're going to copy this. +2, and then +1 for the other one. And then, perfect. So, and then we can copy this and make one for X and Y. And then this we just get perfect. So that's done. And then we're going to do the opposite. So public void right frame buffer. So again, so we're going to turn the index into a subpixel, and then frame sub equals R. Make them 3 of that, and then RGB. So this writes in a whole pixel into our buffer. And then we're gonna copy this, same thing. And then we want int X, int Y, and then copy this. There we go. Okay. So yeah, so now we have filled out this entire pixel buffer for the device side and for the CPU side, which means we don't need that anymore. What is next? I think now we get to write the GPU code. Cool. Okay. So if we run this now, nothing's going to happen still. But we'll just run it to make sure that it's going to build all of this code correctly, and it does. So that means our pixel buffer is done. We'll kill render frame too. We don't need that for now. We actually don't even need the XAML anymore. Okay. Back to main window.xaml.cs. So now that we've initialized the GPU, we're going to want to build our frame buffer whenever the resolution changes. So if inside the render frame, there is that on resolution changed, we're going to set that to a width and height. We're going to set that to a function, an anonymous function that we create right now. And this is where things are going to start getting complicated, but we're going to build out the rendering now. So what we need to do the rendering is we need a thread that's in the background that is, when it starts up, it fills the frame with random pixels. Then it writes to the screen so we can see those initial random pixels, and then for each update cycle it will run the GPU kernel which updates the pixels based on the Conway's Game of Life rules, and then updates to the screen, and then it just continues that whenever the application is running. So we need a couple things in this class. We need the frame buffer itself, so pixel buffer 2D, and it's 1 with bytes, and we can add our GPU folder to the includes. So we got a frame buffer for that, and then for the thread, we need a volatile bool. Volatile basically prevents some optimizations from happening, so that run, whenever any read and any write from the run variable always goes all the way out to memory. It doesn't go to cache. And that means that the render thread can actually read that, won't read it from CPU cache, where it might not have changed even though the memory got written to by another thread. There are more correct ways to do threading, but we're not going to do them. So again, type out thread and Alt-Enter to add the include, which is using system.threading. This works, and it's not like we're going to make people pay money for this program, so it doesn't really matter. Okay, so now that we have those three things, we can create them. So first things first, when the resolution changes, we want to check if there's already a render thread. So if render thread does not equal null, then run equals false, which will kill the render thread. Join, and we're going to wait 100 milliseconds for it to join, and if it doesn't, oh well. We'll let the system crash if it's in a bad state. Again, we're not shipping this code, so it doesn't matter. So if the frame buffer exists, we're going to want to dispose it, because we're about to create a new one, and now we're going to create a new one. Frame buffer equals with device, and we have to put an exclamation point here for device because we know it's there. And then width and height, which is going to create our frame buffer. And then we're going to, so when the resolution changes and we create the frame buffer, we're just going to fill it right here, which we're going to call the fill random function, which we need to create. And then we're going to invoke updating the frame on the UI thread. And so the way we do that in WPF is we get an access to the current application, and we're going to dispatch. We're going to call the dispatcher, and we're going to invoke a new anonymous function. Nope. Thing there, and then this is going to frame.update. So, okay, that's done. I'm like, why is this error? Why does it have an error? You need a semicolon there. Okay, so that's all we need for this. Now we need to fill out fill random. Let me scroll down so I can use my cheat sheet for that. So we're gonna need a random is new random, which is one of my favorite C# things. And then we could use ILGPU's random to generate all the random numbers, but that is a little complicated. And for now, we're just going to do it on the CPU. It's not that slow. So parallel.for, we're going to start at 0. We're going to go to frame buffer.width times frame buffer.height. And we're going to take int I. So if you haven't seen parallel.for, basically what it does is it lets you basically create a for loop, or there's also a for each version, which runs on all of your CPUs in parallel. And so provided you write the code correctly, this is a really quick and dirty way to get parallel optimization for whatever your algorithm is. In this instance, we're going to create a byte, which is alive, and we're going to cast it to byte, and it's going to be random.next modulo, let's say 9 equals 0. So that means 1 in 9 times that's going to be true. And then in that case, we're going to set to 255, else we're going to set it to 0. And then frame buffer. We're going to write to the frame buffer. That. And then we're going to add 1 and add 2. So that's going to randomly assign every pixel to either 0 or 255 based on this right here. You can change out this number here if you want to change the percentage-ish. So right now it's 1 in 9, which is like 11%. You could make it, 1 in 4 and it's 25% or whatever, but I find that 1 in 9 seems to run for a decent amount of time and look interesting. You could even set them all to true, which is just going to immediately kill them all. But anyway, we're going to fill that with random. And now we can actually check, and we should see something, in case I didn't break anything. We do! Hooray! So now we have pixels, but they don't do anything when we press space or update or anything. When we expand the screen, they expand. When we make it smaller, they get smaller. So that's good. Now we need to actually use the GPU for something. So we're going to write the generate frame kernel, which is going to be a private static void function called generate frame. And it's going to take an index 1D, which is the pixel, and then the pixel buffer. So D pixel buffer 2D of type byte. Oh, I already have curly braces. So we're going to count up the neighbors. Int neighbors. And then we're just going to do first we're going to get the pose. Okay. That's output. Oh. And because of the way we're going to loop through to generate Conway's Game of Life and read the neighbors, we are going to just ignore the outer pixel along all edges. And so to do that, we're going to go if pose.x greater than 1, if pose.x is less than 1, or pose.y is less than 1, or pose.x is greater than or equal to output width minus 1, or pose.x, or pose.y is greater than or equal to output.height minus 1. We're going to just return. And so that's going to save us from accessing data that we shouldn't. -1. And so now we need to loop through all of the neighbors. And so we have a center position, and we're going to go down in the x1 and down in the y1, and also up, which is going to give us the 3x3 that surrounds our pixel. Sorry. So we're going to copy that again, and we're going to do that for J. And then if. So now we check if they're alive. So pose.x minus I, pose.y minus j, dot x. We'll just check just the x coordinate is greater than 0. And then if I is 0 and j is 0, then we know we're looking at ourselves, and so we can set if is alive is true. So in this instance, we've read from the frame buffer. We know we're looking at ourselves and it's alive, so we're going to set that to true. Otherwise, we're looking at one of the neighbors and we're going to increment neighbors. So now that we've done that, we can do the actual Conway's Game of Life stuff. Hooray! So in Conway's Game of Life, if you're alive and your neighbors equals 3, or sorry, if you're alive, sorry, if you're dead, if you're not alive, and your neighbors is 3, not 2, 3, you're going to be alive. So output dot write frame buffer index or pixel 255. Otherwise, if you're alive and your neighbors are less than 2, or your neighbors are greater than, sorry, if your neighbors are, wait, did I do that wrong? Might have done that wrong. Yeah. So if your neighbors are less than 2 and greater than 3, then you die. So we're going to copy this. I might have done that wrong in the example code. We'll find out. We're almost done. So you're dead, else you're dead. Am I sure I did that wrong? Hold on. Let's look at Conway's Game of Life. Okay. Any live cell with 2 or 3 neighbors lives. So any so if you're alive and you don't have 2 or 3, so if you have less than 2 or greater than 3, oh yeah, that was right. Okay, I did it right. So if you have, I'm so confused. We're gonna go with it because that's what I have written in my example, and it seems to work. Yeah, if you're alive in that, yeah, dead. Okay. Good enough. So that is the GPU kernel. We're going to find out if I wrote it right or not in a second. But now let's go up back to init GPU. We need to initialize one more thing for the GPU, and that is the actual kernel. So we're going to take this function here, the generate frame, and it has to be a special function that is static. Actually, I don't know if it needs to be static, but it needs to not access anything from your class, which static is a good way to protect it. You need to have the first argument in the function be an index of some type. So it can be index 1D, long index 1D, whatever. And then to create it, we're going to do var generate kernel, or we'll call it the same thing, generate frame kernel device.load auto grouped kernel, auto group stream kernel. So an auto grouped stream kernel is quite the function. Auto grouped stream kernel means that it's going to use the default GPU stream, which is basically the queue of commands that are being sent to the GPU. When in doubt, use the default one. You can do fancy stuff by not using the default one and using multiple, but that's a little bit over the scope of this tutorial. Auto grouped also is something you can do fancy with. So you can manually group your kernel, which basically means when the kernel is called by the GPU, you're going to specify the amount of threads that run together in a warp, and how many warps like that are run, and in what the blocking structure is. I would only do that if you're optimizing for the most performance, you don't really need to do that from the beginning. For now, we're just going to use this and it's going to be fine. I rarely have to manually group my kernels. But if you are interested in the most performance, you want to do that. The CUDA kernel grouping tutorials that are out there, specifically the ones from NVIDIA, are more than enough to teach you exactly what you need to do. For now, we're going to use auto grouping. Okay, and now you got to give it once you load auto group stream kernel and you give it the function, generate frame, and it's going to complain. Can I auto do this? No. Okay. So this function needs type parameters, which are the input arguments for your generate frame function. So I'm going to copy this, paste it in here, and then just delete the names of the arguments. And then it's perfectly happy. Now I'm going to go over to this var and Alt-Enter and use an explicit type. Get rid of the question mark. We're just going to copy this. We're going to delete the action part. And we're going to go up here and we're going to save this. Where did I save it before? Just so it matches. After device. We're going to put that right there. And we'll make it public. I don't know, for good measure. It doesn't actually need to be public. So there we go. Now we've generated the kernel. We need, I think we're so close. Okay, now we need to do the threading. So now we need to actually create a function for the threading. So I forgot. We have one more thing to do in the XAML. Under the window tag, right at the end, we're going to add a key up. And then we're going to, if you hit tab, it'll give you this option to create a new event handler. You just hit enter. And inside the CS file at the bottom, it'll create a window key up function. This will be called whenever you hit a key. And we're just going to check if e.key equals key.space. So if the space key is hit, we're going to start the render thread. So we're going to just run the start function. Nope. Start. And then we're going to create that function. And so this function is going to set run to true. It's going to create the render thread. Date render thread, which is also a function we need to create. Doesn't need to have an object. And then we're going to, the render set thread we want to set is background to true. Basically what that does is when you kill the main thread of this application, it's going to kill the render thread, which is great. It saves you a ton. It saves you from leaking threads all over the place and having to restart your computer a bunch. So that's it for the start. And now the actual render thread needs to be created. We're so close, you guys. So close. So we want a stopwatch to time how long everything is taking. And it's going to complain. So we're going to have to add the using and then while run. So while run is true, this thread is going to do the following. It's going to start the timer. It's going to run the generate frame kernel with when you run the actual kernel, the index that you put in is going to be the amount of threads you want that kernel to run with. And the way that our kernel is designed is that it's going to run one thread per pixel. And so to get the amount of pixels, we're going to do the frame buffer dot width times the frame buffer dot height. And then frame buffer get d pixel frame buffer. So if you remember, this get d pixel frame buffer is going to check if there needs to be an update. If there does, it's going to copy from the CPU to the GPU, and then it's going to return the GPU buffer. Now we need to synchronize the device. So whenever you're doing any calls to the GPU, you don't actually immediately do them on the CPU side. What you do is you add the command to a queue that the device holds, and then it starts that immediately, but it's not done synchronously, it's done asynchronously. And so device.synchronize basically says, wait until whatever the GPU has is done. And so now is when we want to stop our timer because the time is valid, and we're going to try and do something. So what we're going to try and do is this same update function up here, where we get the current application, we get the thread dispatcher, and we invoke a frame update. And the reason why we're going to try and do that is because this is in a different thread. It might run after the application is closed, but before this thread has been closed, which just causes a runtime error. Oh, and we're also going to update the frame time. Frame.frame time equals timer.elapsed.milliseconds. And when we catch, we're just going to not catch with anything, and we're going to set run to false. So we're just kill the render thread. And then timer.reset. And okay, I think we're done. Let's try it. So if all goes well, it builds, which is good. When we press space, it's going to execute all that stuff on the GPU. Let's see what happens. Nope. What about now? Nope. Interesting. So we will pause here. We'll put a breakpoint on window key up and see what happens when I hit it. Okay. So the key is definitely hit. It's going to run start. What's happening? Running the render thread. Great. Put a breakpoint there. Does that ever run? Does this ever run? What's going on? Okay. So let's run it again. Okay, so it receives the key press. We'll hit step into. Does that, creates a new thread. That's done. Okay. And then, so now we know we're back. Okay. So it creates the timer in the new thread. We'll hit continue. While run is true, so it should go into that. Starts the timer, runs generate kernel. It needs an update, so it copies the stuff. It's good. Device.synchronize, timer.stop, try. Put a thing in there. Interesting. Okay. It's not updating. All right, so now is a good way. Did I fuck this up somehow? Maybe this is always returning. Maybe that's what's happening. So now I'm going to show you the way to debug all of this stuff. So when you initialize the GPU, set that to true. And what that's going to do is in this function, it's going to force the CPU to be the device that we get, which best thing about ILGPU means we can debug. So I can put a breakpoint, let's say here, and we can see if this for loop ever runs. And my guess is that it doesn't. So again, we get here, we press space. It does run. Interesting. So we can just follow it down. Reads the frame buffer, gets the size, goes there, and then it just skips out. Okay. So let's put a breakpoint here, here, and here where it writes to the output. We'll hit continue. So yeah, it's writing all zeros. That's great, writing all zeros. Does this work? Okay, let's get rid of the breakpoints. Let it run. See if the CPU can run. No, the CPU can't. The CPU can run, but it doesn't change anything. Okay, I know it can't be. Is it not writing to the frame buffer? Maybe that's what's happening. So it should write once. And if we hit continue, we can see that it's written once. And now when we hit space, it should try and write again. And it does. The length is correct. Writes the back buffer, does the unlock. Oh yeah, we know because it was writing the frame time too. All right, let me look at my code and see if I do the back buffer, lock, do the back buffer, data 0, back buffer, data. Make sure the rect is set correctly with height. Yep. Okay. All right, now another debugging thing you can try is we know that this is running, right? Yes, this is running. Okay. So here, let's make it magenta. So 255, 255. We know that's running. Continue. Okay, so it's set. It's running, but it's not making it magenta. Maybe I'm not copying it. So let's go back to pixel buffer. And then we'll go here. Let me check my cheat sheet. Get frame data copy to CPU. Needs transfer false. That's correct. Get buffer needs update. Copy from CPU data needs update false. So let's make sure this all ever runs. Yep, we know it's writing to the thing. Okay. Yep, so we know it should be copying the CPU data, which we can see has random data. So we'll hit continue. That's great. And it's never updating needs transfer. Oh, I see what happened. I wonder how many of you noticed this. That needs to be set to true. Now it's going to work. Now we should see purple when we run. Oh, that's terrible. Let's turn that off. Okay, so we'll change that back to 0, that back to 0. Run it one more time. Perfect. Okay, so that's running on the CPU, remember, because we're still debugging. So let's run back on the GPU again. Go back to init GPU, hit false. I can type. So now it's running on the GPU. We'll make it big. And it's instantaneous, which is both awesome and terrible because we can't really see it updating. So we're going to add in the render loop, here in update render thread, we're going to add a thread.sleep for 250 milliseconds, which means it's going to update at 4 FPS. Okay, so now that we add that sleep, we're going to run one more time. It'll run at 4 FPS. Again, make it big. There we go, Conway's Game of Life. Next video, we're going to work on the spatial hashing algorithm and filling up a voxel grid. And then we will, I don't know, we might have to do it in 2 parts. We might do it in 1. We'll see. Let me know if you have any questions. I'll be on the Discord. And yeah, hopefully this is helpful. One thing I forgot really quick, there'll be a link to the Discord and to the code on my GitHub in the description or wherever you find this. So